In this video, we will talk about a common error when using L'Hopital's rule. So I want to begin with an example that I'd like you to try first. So we have this limit. Take about 1 to 2 minutes to try this problem. 4, 3, 2, 1. Pause the video. Pause it for a minute or two to try this question on your own first. Alright, so hopefully you've done that. Hopefully you've paused the video and tried this for a minute or two. Let's go ahead and talk about it together now. So I want to mention what this common error is, and then we'll talk about what's wrong with it, and then what's the correct way to do it. So here is the common error. So if I use L'Hopital's rule on this, so I got to write LH over my equal sign to indicate I'm using L'Hopital's rule. So I got the limit as x approaches 0 from the right. The derivative of the top is 1 over x. The derivative of the bottom is e to the x. Okay, I've already made a mistake. So the question I want to ask now is, what's the error? So what is the error that we just made? The error with this, so here's the answer, is that when we look at the limit as x approaches 0 from the right of ln of x divided by e to the x, the first step for evaluating any limit should be we try to plug in. And if we try to plug into this, ln of 0 from the right, this is where it's helpful to remember, what does the graph of ln of x look like? Hopefully we know by now, because we've been seeing it since chapter 2, I think, is when we first reviewed what the graph of ln looks like. But we've seen it since then a bunch of times. But I know it may have been a while. Okay, so ln of x graph looks something like this. And this is the x-intercept. It's at 1, 0. So as x gets really close to 0 from the right-hand side, that is this part of the graph. X is getting really, really close to 0 from the right. And as that happens, the y values approach negative infinity. So that's what the limit is. That's what the limit of the top is. So the ln of 0 plus is negative infinity. And on the denominator, there's no issue with just plugging 0 in. E to the 0 is just 1. So the problem with doing L'Hopital's is this is not one of the forms we can use L'Hopital's on. This is not a form we can use L'Hopital's LH on. We can use L'Hopital's on infinity over infinity, or maybe with negatives like we have here, or 0 over 0, but not negative infinity over 1. In fact, we don't even need L'Hopital's for this. Negative infinity over 1 is something that we know what it is. Negative infinity divided by 1 is just negative infinity. That would have actually been the correct answer. Okay. So I point this out. I point out this common error because I see this a lot. This is probably the most common error I see people make when doing problems with L'Hopital's. Usually people get so comfortable with L'Hopital's that they think that every limit can be done with L'Hopital's. But that's not the case. The key takeaway from this is we can only use L'Hopital's rule if the limit has the form 0 over 0 or plus or minus infinity divided by plus or minus infinity. That is super, super important right there. All right. So let's look at another example. So with this problem again, I want to give you the opportunity to try it first. So this time, pause the video for about 3 minutes to try this one. 4, 3, 2, 1. Pause the video. Pause the video this time for 3 minutes to try this question. Alright, so hopefully you've done that. Hopefully you've tried it for about 3 minutes. Let's talk about it together. So the first thing that I want to do is I want to try plugging in. Okay, I want to avoid making that mistake from last time. Let's plug in to make sure it's a L'Hopital's thing. Okay, so if I plug into this, I'll get 0 on the top, and I'll also get 0 on the bottom. Alright, so we can do L'Hopital's. So this equals, I write LH, because I'm going to use L'Hopital's. So we have the limit as x approaches 3. Taking the derivative of the top, we get 2x. Taking the derivative of the bottom, we get 2x minus 6. Okay, so first, I'm going to do this wrong and see if you can catch what my error is. So first, I'm going to do this wrong. All right, so let's do L'Hopital's again, because I'm not quite done with this. If I do L'Hopital's again, I get the limit as x approaches 3. The derivative of the top is 2. The derivative of the bottom is also 2. That's kind of nice. And then 2 over 2, that just becomes 1. So what is wrong with that? Pause the video for just 30 seconds this time and see if you can figure out what's the mistake I just made here. 4, 3, 2, 1. Pause that video. Pause it for about 30 seconds to think about this. All right, let's talk about it together. So the reason this is wrong is I made the same mistake that I talked about above. L'Hopital's, LH, doesn't apply. It doesn't apply to this limit. I needed to plug in first to see, is that something that's L'Hopitalable or not? So if we plug in our value, if we plug 3 into this, we get 6 on the top. On the bottom, we get 0. But 6 over 0 is not something I can use L'Hopital's on. It's not one of our two forms, 0 over 0, or plus or minus infinity divided by plus or minus infinity, that L'Hopital's can be applied for. Okay, so I'm going to bubble this. So this is another example that I've done where I've sort of talked about falling into this trap, and I really want to avoid trying, doing that. It might happen to us here and there, but each time that it does, we really want to, look at it carefully so that we can hopefully try to avoid making this mistake in the future. All right, so when we have something like 6 over 0, non-zero on the top and a 0 on the bottom, we got to go back to our Chapter 2 strategies for limits. This involves taking one-sided limits. One-sided limits, we got to take those. Okay, so let's do the limit from the left and then the limit from the right. So from the left, we get the limit as x approaches 3 from the left of 2x over 2x minus 6. So when we plug in, there's no issue with just plugging in 3 into the numerator. There's no problem there. That just gives us 6. On the denominator, there's a problem if we plug in 3, just straight up, because we get 0, and that gives us something that's undefined. So that's where I have to think carefully about what does it mean for x to be approaching 3 from the left. That means x is a little bit smaller than 3. And if x is a little smaller than 3, the denominator, 2x minus 6, like if x is a number like 2.9 or something like that, the denominator is a little bit smaller than 0. So I would write 0 with a little negative sign to indicate, oh, it's close to 0, but a little smaller than it. All right, so this is, the top is positive, the denominator now I know is negative, that's going to give me negative infinity. Let's do the limit from the right. So from the right, we get the limit as x approaches 3 from the right of 2x over x minus 6. Again, for the same sort of reason, the top is 6. And this time, because x is approaching 3 from the right, x is larger than 3. Whoops, I forgot to write the 2 here. 2x minus 6. X is larger than 3. So plugging that into the denominator will give us something a little bigger than 0. So I'll write 0 with a plus sign. All right, so here this is positive infinity because the top and the bottom are both positive. All right, so we got these two one-sided limits. Therefore, the overall limit, the limit as x approaches 3 of 2x over 2x minus 6 does not exist. We would write D and E. Does not exist since the, I gotta write the reason why, since the one-sided limits are different. Them being different means this limit doesn't exist. All right, so returning to our goals from this section, we've now discussed a common error when trying to use L'Hopital's rule, which is make sure we actually have a limit of the form 0 over 0 or plus or minus infinity divided by plus or minus infinity. If we don't, if our limit doesn't have those forms, I can't use L'Hopital's rule. All right, so in the next video, we will talk about how we can convert other indeterminate forms, things like 0 times infinity or infinity minus infinity, into a form that we can actually apply L'Hopital's rule to.